here. We'll take a look at some malware. So I'm covering, actually measuring the entropy of some of the document code, or the code I've been extracting out of documents. My name's Adam Hogan. I'm a security engineer at Cisco now with the Advanced Threat Group, which means I'm actually sort of a technical liaison to the sales field. So anybody in, like, I don't know, the nearest 7 states, give or take, if they're working on a malware project, they'll actually have me come in case the customer knows what they're talking about, and you have to get a little deeper than usual, right? So what I want to do today is actually briefly talk about, like, some of the document malware I'm talking about. We'll actually take a look at extracting the code out of documents, so you don't have to go fishing for it, but actually, like, extracting the actual runtime from an otherwise normal document file, Word document or PDF, something like that. And I'll go briefly over information theory and what that is, because it's there's a central tenet to information theory that I'm using to measure the entropy of the code I'm extracting. We'll get into what that means, because now we can actually extract some data, run some mass statistics on what we're collecting, and take a look at this. So I'll have some statistics on the actual malware I've been collecting, and how we can sort of differentiate that, and turns out there's a way to actually detect some malware by running these algorithms. And then, in good fashion, I'll show you how to get around the detection I'm talking about, right? It's a pretty minor extension of the theory, and of course, that's the reality of being on a blue team, right? Everything evolves, and if you want to understand this stuff, then it's important to understand the weaknesses as well, because if you don't, the bad guys are going to figure it out. In fact, I'll extend the talk a little farther than I thought, because I already found some malware that's totally getting around this stuff. And like so often happens when you're analyzing malware, you often find that the bad guys got there first. So I wrote up the talk thinking this is just such a great idea. I was patting myself on the back for having, oh, this is going to detect malware. And once I actually dug into the data, it's like, oh man, they figured it out. All right. So first, when I say document malware, I'm basically mainly talking about, say, the stuff we see running in, like, our Office documents. So the VBA code embedded in there. Or if you take a look inside a PDF file, that could have God knows what, right? Mainly JavaScript is where you see a lot of the malware hidden there. But of course, you can have Flash in there. You can have all sorts of crap. Because PDF is like on paper, PDF is like this close to being an operating system, basically, for all the kind of crap you can put in those. So there's all kinds of stuff we might get out of a PDF. And this actually started when I was helping a customer out with a really bad Dridex infection, right? So this was getting that Cridex rat in through these document files, right? Here's an Excel sheet, here's a Word document. Hey, please open this. And when they did, of course, they got infected. Now they have this awful remote access Trojan that's allowing all sorts of bad stuff into their organization. Customer I was working with was just absolutely riddled with the stuff, so we were looking for any and every way we had to go and track the stuff down. So that's really how we got started. Quick example then. I mean, let me take a look at some of the ways we can analyze this stuff. So in this case, what I have is a PDF. Does this show up well? Contrast on that should be better, huh? All right, so I have a PDF document actually made with Metasploit, right? So loaded up one of the PDF exploits in there, right? Regenerated it. If you open up this PDF file in the right, or should I say wrong version of Adobe Reader, it's going to call home and try and establish a shell for you, right? Well, so if we're actually taking a look and analyzing this, the way I'll usually start if I'm just doing like one file at a time, is I'll actually use Claim AV, which, I mean, mostly known as an AV product, but truth is it's a hell of an engine to analyze things. Because in order to be a good AV, in order to get to the point where you can use whatever signatures you have to scan, you have to sort of normalize traffic, and it excels at that. A little better than, say, when you're just running static signatures across whatever, right? Claim AV does a lot to normalize. It'll unpack binaries, right? It'll normalize a lot of traffic. and a lot of documents and things like that. It's also going to extract weird objects in these files. So if I run a scan here against my PDF file, what I've done is I've turned on a bunch of extra flags to give me all the debug information. CLAM usually runs all this stuff in the background because 90% of people are using CLAM to just find viruses and quarantine them, right? Well, it's doing a lot in the background, and if you take a look at some of the stuff that comes out, well, one, I mean, we did get a hit, right? So one of the signatures did hit a heuristics. It actually says, hey, there's obfuscated code in here, right? It doesn't come back and say it's malicious. It says it's obfuscated, which is, of course, how bad guys use to hide their stuff. But you'll also see when it starts finding different objects in the PDF file, it's extracting them. And if you ask CLAM nicely, it will leave the extracted files after it's run through and scanned them. So if we now look in this directory, we'll see there's a couple extra files there. Actually, one's a directory. And if I go in, not that one. If we go into that directory, you'll see there's those objects. What it's done is extract each object that was in the PDF file. And if we take a look at them, like I'll run file on all of them, we can see a couple of them are empty, right, which is typically the case of commodity malware. If this was targeted, they wouldn't be empty. There'd be text in there. There'd be more ASCII because there'd be something in the document file to actually address it to you, right? If you open up this PDF, it's blank, right, like most commodity stuff. But you'll also see that PDF01 is ASCII text. If we take a look at that, that's all binary, right? But if we run that back through a hex editor or a hex dump, nope, I screwed it up. We run that backwards through a hex dump, we get JavaScript code. Really shitty JavaScript code. Right? Take a look at this. I mean, this is how it starts, right? It uses the unescape function, and then all the actual code is encoded, right, in Unicode. Doesn't change how it operates, but it does make it so you can randomize it, and it makes it so you can't really write a static signature to hit on this stuff, right? So your IPS, your AV aren't going to be able to track this stuff down. But of course, just glancing at it, we can see this looks like nonsense, right? So actually take a look at some of the code that runs. Like, okay, here's a for loop, right? For, and then what happens until, set that variable to 128. Some of you don't know JavaScript, and you're looking at this and saying, that looks like complete nonsense. Some of you do know JavaScript, and you're looking at this and saying, that looks like complete nonsense. You're on the same page, right? I've written some pretty terrible code. I wrote a lot of Perl back in the day, comments or for wusses, right? All that crap. I've never written anything this horrible, right? Someone went out of their way to make this illegible. So like do a search and replace on all the variables to come up with absolute random nonsense, right? And this is a fairly common technique in people writing malware. You have all this random nonsense. So can't we look for documents that have code that's made up of random nonsense? Isn't that something we can go and look for, right? So that's where we come to information theory. It's actually the branch of mathematics to actually define how to measure information in a message, which actually started by this guy, Professor Claude Shannon. I actually wrote a paper called The Mathematical Theory of Communication, which is probably up there with one of the most important pieces of research ever written. This guy actually put together how to measure digital information, which at the time was working out, how much data can be processed over a given communication channel, right? He did a lot of theory on, can you have perfect encryption? That can't be broken. And he was working at Bell Labs at the time, like alongside Alan Turing. They'd have tea every day and talk about how to program computers. Which, keep in mind, the transistor hadn't yet been invented yet. They literally sit down and talked about how to program a computer that hadn't been invented yet. So this is pretty incredible stuff they were working on. Now, it turns out the secret to measuring information actually comes down to measuring surprise, right? If you want to measure how much information you're getting, it's the amount of surprise you're getting from an information channel, which is a little weird to wrap your mind around at first. But say we have a theoretical machine that every hour spits out the number 1. Every hour spits out the number 1. Number 1, number 1, number 1. You wait an hour. You wait and see what's going to happen. It spits out the number 1. What have you learned? Nothing, right? If you can totally predict something, you don't learn anything from that information. So it's actually the amount of surprise you get from data that measures its information content. And the way we measure that is entropy. Now, everyone's probably heard of that in the context of physics, right? In physics, entropy measures the uncertainty about a physical system. We have one state and many of many possible states. Although, if you're looking at the way of the universe, we also see that determined as like chaos, right? Entropy means everything's falling apart and going to shit. It's not that, but in a very technical, mathematical level, it doesn't mean everything's going to shit. It means that it's a random process, but of all the many states the world could be in, most of them are shitty. So it's actually just that we're following a random process, and things being orderly is very rare. Now, to an information theorist, it's not that different. And entropy is really about the uncertainty of a message. I'll imagine what's the possibility of one message among all the possible messages that could be sent. And when you get that down in paper, it's basically the same thing. We talk about order versus information, but they're essentially the same, because if everything's orderly, if everything's in perfect order, there's no surprise, there's no actual information being conveyed. So entropy is really it's measuring the amount of surprise we're getting from data. How random is it? And as we saw from the malicious code extracted from that PDF, we're looking for stuff that's been completely randomized, because that's how the bad guys are hiding their attacks. Then another way to think about entropy would basically be the average number of yes/no questions it would take you to guess an unknown message. Right? So how is that measured? Here's the actual formula for it. If you remember physics, this is going to look familiar because it's written the exact same way in a physics class, except they call it S instead of H. That's literally the only difference. And it's not a coincidence. The actual math behind that is the same for a reason. And I'll get into that in just a bit. What we're going to do is actually look at the negative sum where you take, so P sub I is actually the probability of each state in a system. Right? You multiply that by the log of that probability. And then add those up to get the total entropy of whatever you're looking at. You see the logarithm is usually base 2. In math theoretics, sometimes you'll see other bases. Sometimes you'll see 10, sometimes you'll see E. Base 2 is certainly the most common. Anywhere you're talking about computers, it's going to be base 2. So anything we're looking at is going to be base 2. In math theoretics, you'll see the unit then labeled as Shannon's, right? Named after the guy that did it. How many Shannons of entropy is that? But his word was that if you did it in base 2, we were actually looking at binary digits, which he shortened to bit. Right, which is actually in that paper I mentioned before, it's actually where the word comes from. It was the first time it was published. He actually gives it credit to a colleague of his there at AT&T Bell Labs, but nonetheless, that's actually where the word comes from. So I mentioned the equation is essentially the same in information theory as it is in physics, and that's not, turns out, a coincidence. The underlying I'm getting way out of my depths here, but the underlying apparently reality of the world is that information and entropy are essentially the exact same things. The physical state about the world, about how things are able to process at a quantum level, is essentially an information theoretic process. To the point where one of the active debates in physics, and where physics and information theory overlap, is whether or not black holes destroy information. Right, so we're actually getting that down to that at a quantum level, which I barely understand, but enjoy reading because it's just one of those kind of blow your mind things, like how connected is the universe. So I pulled the graphic there from Interstellar of a black hole, which in itself is a fantastic, just that this exists. The people that made the movie actually hired physicists to run, I mean, they got literally like a rack of CPUs and had it simulate what a black hole looks like. No one had ever stopped and think, what does a black hole look like? They actually ran these simulations, come up with this. Physicists had never thought about it, they're like, well, yep, that's what it would look like, right? So we actually have it going down there, and you have all that entropy being collected there. The question then is everything being destroyed, and with it information? It loses me at that point. But hey, it's neat. So how do we use that formula? Well, consider flipping a coin, right? If you've got a coin, this is me holding up a coin. I don't actually have one. I mean, anyway. You got a coin, and you have two states to that, right? Because we saw we wanted to measure up P sub I. Well, here we have P sub 1 and P sub 2, right? Heads or tails. There's two different states a coin can be in if we're flipping it, right, as a random process. The probability of either state is 1/2, right, 0.5. The base 2 logarithm of 1/2 is -1, and then we would multiply that, sum it up. So we actually get the entropy of a coin flip is 1 bit of information, right? So a long way around what you guys would have already known. If you have a switch that's on or off, that's 1 bit, right? That's the actual entropy of that situation. Now, if you've got, say, 32 bits to work with, if you're using 32-bit alphabet to encode data, you actually get 5 bits of entropy associated with that. That's how much information can be stored in that. Or say with 1,000 characters, using a 32-bit alphabet, you get 32 to the 1,000 power possible messages, and the logarithm of that number is 5,000. So we just come back to, right, 5 times 1,000 to measure the amount of information being stored in that possible message, right? Now that we can measure that, we can look at, say, how redundant a language is. So my question there is, can you read this, right? Shannon actually estimated that English is about 50% redundant. That not every bit of, not every letter of every word is actually conveying information. A lot of it's redundant. So if I take out a few letters, can you still read it? Now, let's bring that back to malware, right? How do we actually analyze malware at that? Well, first of all, I pulled out this quote, so I'll throw it out there. It is probably, this is what JCR Licklider, was apparently a contemporary of Shannon there at Bell Labs, who said, it is probably dangerous to use this theory of information in fields for which it is not designed, but I think the danger will not keep people from using it. So a fair disclaimer, that I might be talking on my ass, but suck it, Licklider. We're going forward. Because here's what I'm doing. I'm taking a bunch of malware I've got. I'm in the process of doing more. I started with a fairly small sample, which is just Office documents. So I have about 10,000 samples. I'm currently working on processing. The results today are actually based on 1,024 samples, my original slice of this data, for which I extracted code without going back and seeing why the code errored out and why I wasn't able to extract the code. I still had 305 malicious samples left. I pulled the code out of those Microsoft Office documents, and I measured the entropy using the formula we just went over. How do we do that? Well, it's actually turned out to be one pretty simple in Python. They already have an entropy library. There are already libraries for extracting codes from Microsoft Office documents. So if you check that out, OLE tools, there's a library in there called OLE VBA. Fantastic tool. Even if you don't know Python, you may still want to download this because you can run it as a command line script. You can actually run this tool and give it a document format or like a directory full of documents, and it'll give you a quick summary of which ones have VBA in them, right? Which ones are making some suspicious calls. And so a really great tool. And then of course you can dump out the code from there. If you load it like a library, you can use its functions to run through and process it, which is I did. So really all I had to do is import these functions. Say, okay, here's my file, run it through the VBA parser, I saved out the code, and then I could pass that to the Shannon entropy function, which returns the measure of entropy of that code. Right? So that ran for the 305 samples. I got back the results. The mean entropy was 5.28, with standard deviation of about 0.25, which is fairly high. If you compare that to, say, a couple benchmarks, completely random data has an entropy of a theoretical limit of 8, right? If you run like a number generator, you usually come out like a little over 7. But the theoretical limit for measuring entropy is 8. So if you have completely random data, you're about 8. And then English, the entropy of English is like the English language is about 2.6, right? So in theory, because all the letters we have in English, it should be closer to 5. But because there's a lot of redundancy in English, it's actually closer to 2.6 when you measure it. But are those good? That's not exactly a good baseline, right? Because English isn't exactly code. So what I did was actually gather every other script I could find to measure the entropy of non-malicious code, so we have a comparable baseline. Right? I have all this malicious code with entropy on average of 5.28. Well, I can't just compare that to the English language, right? VBA does look different than English. So I need more standard comparison, so I actually grabbed all the scripts I could. and then measured the entropy of that. And when we look at the non-malicious code, the average entropy was 4.75. So when we compare there, there's a fairly significant difference between the entropy of malicious code and non-malicious code. And for the more statistically in mind, I was actually able to run those tests. It is statistically significant if you do like a z-test, comparing the difference in mean of these two series of data, the entropy of malicious code and non-malicious code. They were absolutely statistically significant, far greater than 99% chance, right? So, significant difference there, so we're saying, okay, there is a difference here. We should be able to calculate the entropy of new documents now, and quantify them, and identify them, if not as malicious, as certainly as something suspicious. Here's what that data looks like. So this is the same data on both graphs. Originally, it's just the raw entropy, so the vertical one is the actual entropy of, so as it goes up, we have a higher entropy, it's more randomized. And lower down, we have less random data. Here on the left, is it on a single dimension, right? Because all I have is the entropy. Here I've got it spread off, not just the entropy, but also a number of observations. So the horizontal axis doesn't actually mean anything. It's just a way to spread out the data, right? Because it's all clumped together here. Now we're kind of spreading it out, and we see some interesting things, actually. Because there are a few clusters here, and those kind of things are fairly interesting. For one thing, if you look on this horizontal line, there's a bunch of them grouped right there, which is something you need to go into a lot more exploration of. Because you highlight that, what we have is a lot of documents that have essentially the same entropy. So you pull out the code, they have the same. Yeah, question? Yeah, yeah. So the farther they are on the right, that doesn't mean anything. It's just a way to spread out the data to get a better look at it. Yeah, no, good question. Because here, on the left, you can't see, there's this kind of bolded X, right? But you don't see that there's actually a bunch of them there. And here it actually looks fairly suspicious. I'm fairly certain we can take a look at that and start tying families of malware together. Because if we have a bad guy who's saying, okay, I've got my malicious code, I want to avoid AV, what I'm going to do is take the same code and randomize it a bunch of different times. Well, if you're using the same randomization algorithm, you're going to come up with roughly, if not exactly, the same entropy score for that code. So by looking at clusters on this sort of graph, we may actually be able to identify, hey, this is all coming from, if not the same malware author, the same algorithm. All right. And of course, if we're not sure where it came from, we can always pick a default answer. All right, so how am I doing in time? I talked about how we could actually measure this and how I'm actually picking up code and how we're actually able to come back and say, okay, once we've done this, we can pick out malware, right? Because now as we get new files in, we'd actually be able to pull them, measure the entropy, and then based on its actual level, we could say, okay, what's the probability that it's different from the mean of all the malicious stuff we have, right? And when I looked at it, like the threshold I now use, like statistics aside, when I pull a new file, a new malicious file, and I just run the entropy of that code, if I get anything greater than 5.2 back, then it's likely encoded. Right? It's likely, and the more you look at it, there aren't good guys out there randomizing their code for the fun of it, right? I think I've seen one sample that did that, turned out to be legitimate. So you've seen some? All right, I've seen one. I've seen like JavaScript that was a test-taking software, and it was all client-side. So they randomized the code so that the students couldn't figure out what the answers were by viewing source, right? So there's some stuff out there. But when I look at VBA macros that someone's hidden in an Excel sheet, I don't think there's a lot of randomization going on there. In executables, there's a lot more of that, right? There are legitimate reasons to pack an executable and things like that. But if you look at the standard reason people write an Excel macro in the first place, not a lot of reason to randomize those. So now we start measuring that, start detecting new malware as it comes in, right? So, of course, it's not, it's not groundbreaking in the sense that when I pulled up that malicious code in the beginning, you could look at it and say, hey, that's totally malware, right? Just by looking at it, you knew it was randomized. But of course, when you were analyzing malware in bulk, you're probably looking at hundreds, maybe thousands of samples a day. You can't look at every one of them. So this is another one of those tests you can run through. Say, okay, find the suspicious stuff that I want to spend time on, right? Because at the end of the day, that's what a malware analyst has to work on. I mean, half of your workflow has to be how do I prioritize my time, because you can't run every sample through IDA, right? You can't do it. You have to be fast at that, so you have to get into a system of, okay, I need an automated process to identify the weird shit that I need to look at, right? So that's why we have tools to run statistics, to run it through CLAM and things like that, to find those heuristics, to find out the weird stuff. One, find out the stuff we already know is malicious, so yeah, okay, deal with that, delete it, quarantine it, let's move on. The stuff that's absolutely good stuff, and now show me the stuff in the middle where we need a human to take a look at it, right? And that's the reality of going back and forth with the people who write malware. There's always going to be new stuff, and when you're at that cutting edge, it's probably going to take a human to sit down and look at it, but hiring someone to analyze malware is expensive, and there aren't many people out there who can do it, so you have to do as much automation as you can. So, now that I've got this great new way to detect malware, how do we get around it? So I'll talk about that. One, because the blue team, you have to keep in the back of your mind the bad guys are working around and getting around everything. And if any of you are red team members, this would actually be a fairly minor tweak to Metasploit to go back and fix how it randomizes the malicious code in order to get around any detection like this. Okay? So, how do we decode data, right? Now, I talked about how when we measure entropy, we find that the English language has some redundancy. Can anyone not read this message, even though I've randomly selected a letter and removed it from it, right? Pretty obvious, right? Well, there's a lot of reasons for that. One, there's only so many possibilities. You know a whole lot of words and can compare the options. Also, the Q and U go together almost always, right? So in that sense, that's one of those lack of surprises that indicates little entropy, right? If you see a Q, you know the next letter is going to be U. It's one of those code breaking tricks. Like, have you ever sat down, like, as a kid, you had a workbook where they just, move one letter forward and you had to go and scramble it, something like that, right? Letter substitution, basic ciphers, right? If you figure out what Q is, you probably know what U is, right? Because they're so always linked. So they go together. Letters in the English language are not all created equal. They're not used at the same frequency, so that Q and U usually go together. Now, all those letters are not created equal, right? So we have certain strings that go together. We have certain patterns in letters, so that even if we're missing part of the message, we can still usually figure it out. So we know how those go together, and we can start to piece that together. Of course, luck be in the air tonight, right? What were you thinking? Here is some completely random code. What we've done is, so this is called a zero-order randomization. And what this is randomized for each character, right? Randomly select a number between 1 and 27, and select a letter, of course, and then like 1 for a space, right? So that's what we've done here. You look at this, you know right away it's nonsense. Right? This looks like random crud, right? And it is, because we see all kinds of stuff. We see, Q's and Z's in there with greater frequency than we would ever see in real language. We've got some really long words, right? Because the space is as likely as any other letter. So we've got words that are frankly just longer than we usually see in most text. This looks random, right? So just like we pulled up that JavaScript at the beginning, it was obviously random. We can look at this and see, similarly, this is awfully high entropy. On the other hand, what if instead of selecting a letter randomly, we did it based on the frequency at which that letter is used in the English language? What if we selected E more often than Z, based on how often we actually see it? In that case, we get this a first-order randomization. So we'll see, and if you compare them, obviously random, got to look at it a bit more, right? You spend a little bit more time looking at this, of course, it still looks random, but not as random as that, right? So we can do that. Now, so what we're doing is selecting letters based on how random they're looking. Instead, this moves up to a second-order randomization. So what we're doing now is instead of selecting letters based on their frequency, we're actually looking at pairs of letters and how often they appear in the English language, right? So we actually extend that beyond a certain letters, and what we do is we select a random number, and then we go to our state table and select a pair of letters and group those together, right? So I don't remember much of this, but like off the top of my head, TH is the most common letter pairing in the English language, right? If you see a T, it is more often not followed by an H more than any other letter. And we would want that to reflect in our randomization process. So again, if we do this for not pairs of letters, but 3 in a row, including the space, we have something that looks a little bit more like real language. So in this case, we can see the length of the words is getting to a more normal platform because, again, the space is included as a character in these series we're randomizing. And then, by the way, we don't even have to select letters at random, right? Why not just use the random generator to pull the dictionary file you've already got in your computer? So in the case here, we have a first-order word randomization. The words are selected at random from the dictionary. Sorry, not random. That would be 0 order. If you just randomly select words from the dictionary, you have a 0 order, first order, roughly tied to how often these words are used. So you see, the in there, you see to a couple times, but you also see some weird forms like it says 2 of 2, things that wouldn't go there. So once again, we can up like what words often go together, and we can do a second order word approximation. And we do that. I mean, it's if you try and read it, it's obviously nonsense, but if you just glance at it, it might just look like English, right? So at least we're getting the capability. Do I have a third order? No, I don't. So, and then third order, you really get to the point where it's probably even better than like your typical like lorem ipsum crap that like fills in blank documents, right? At least looks like language. So if you were going to, say, take your malicious code and you wanted to randomize it so an AV or an IPS couldn't detect it, why generate your variables out of random characters? If you did it with some frequency or you just selected words that are common, you'd actually get to the point where this sort of entropy detection and anomaly detection in code might not hit on it. Right? But also, I've been talking this entire time about measuring the entropy and character frequency and all that of the English language. First of all, code is in English, and by the way, if you don't know this or not, but not all the people writing malware speak English. And in fact, since I was working through all these Word documents, a lot of them are Russian, right? And I don't spend a lot of time in attribution, but if I dump like your Excel sheet and it doesn't say sheet 1, if there's Cyrillic, I'm like, hey, that's Russian, right? That's the extent of my attribution. I don't spend that much more time on it. But hey, if it's in Cyrillic, I at least say that's going on. So we know, in a shadow of doubt, that a lot of malware isn't being written in English. So it might actually be horrendously biased of me to focus on English in order to do these approximations. And as I mentioned in the beginning, we might actually find that the bad guys are a step ahead. So the question would be, are bad guys really looking at this? And then if we do have a cultural bias in language, what can we do to randomize this stuff that actually transcends language? Which would have been the next step. Unfortunately, the bad guys beat me to it. Going through the code, I actually found some really interesting stuff. So, go back to my data, where we saw all the different levels of entropy I measured, right? Up at the top, we have documents that are heavily randomized. We have most of our stuff coming in the middle right here. We had that really interesting group there that I think is probably all going back to the same threat actor, but what about the stuff at the bottom here? That has some really low entropy, especially compared to VBA scripts, especially compared to all the other malicious code we're looking at. This is a couple of standard deviations outside the norm for the malicious code I was looking at. So I grabbed a couple of those to find out, okay, well, why are these different? What makes them different? So first example, this came back with an entropy of 4.74, which is quite a bit outside the threshold for what I'm looking at to determine, is it randomized? And we'll find out they have a way to build in some extra code in there to get around some detection like this. So I have a few shots of this code. What it is doesn't actually matter, but you'll see like some of the functions, add customer, and there's comments. So they actually have comments in here to set up the form and then show it. So you'll see functions here to like read data from this Excel sheet. And then add some buttons to just, add or cancel. So they've got a little form built in this Excel sheet, so you can add a customer to it. All right. Next one, yeah. So there's our add customer function. All right. So fairly normal stuff. Has anyone written like Excel or Word macros before? I mean, this is the kind of stuff you end up doing, right? You work in like it's my first coding job actually was writing Excel macros. To help speed up processes that people were doing manually, which got my car keyed and got threatened. The automotive industry is not a good place to replace people with automation. They're really sensitive to that. That was interesting. Anyway, we can see we've got other functions in here. Like it's not only is there an add customer, there's an edit customer button. So we can read data back in there, actually read data from the spreadsheet, and go back and pass that through the edit function. So this actually looks at parsing through the data. Here we have functions to show all customers. All right, check out what the active sheet is. If filter mode, show all data. What's filter mode? It's not a variable that's ever referenced later. It's never set, So we see this actually sets up and it reads the name and the phone numbers from the Excel sheet, but the sheet is blank. There's no data in it. There's no data for it to read. And those functions are never called. They're never invoked. They're never initiated. There actually is no way to kick them off. Even like if you were to go into that Excel sheet and try to put data in. It's all code that is never used, right? So they've just plopped in a bunch of code that does nothing, essentially, along with their malicious code. Because if you keep digging into it, well, in the middle of all this code comes these functions. Right? So if you've seen malware before, these are going to look a little more familiar, right? This is where they're actually doing their obfuscation, right? They use the character function. So you can actually write your malicious code out the long way. Instead of writing your malicious code, encode each letter back to its ASCII number, and then pass it back through the character function to turn it back into a letter, right? So all it's doing is turning it back and then forward. It's not something useful, but it does hide your code from anything that has a static signature that's looking for it, right? So here we can see, again, this is the exact kind of obfuscation stuff we see with malware all the time. This is clearly malicious, but my statistical method for measuring it is going to fail because they've anticipated some sort of measurement like this. They've built in a bunch of fairly normal-looking code around their malicious code. Even though that normal-looking code will never do anything, it's there just to throw off anyone trying to do similar detection. And then there's one part I really liked here. After they get through loading all the malicious code in these functions that are going to decode it, they don't directly call the malicious code. Instead, what they do is they set on error go to this function here. That's the start of the malicious code. All right, so they set that up, and in case there's an error, go to that, and then they run this: a equals 129 divided by 0. So they don't even directly call the code. They set up as an error and then divide by 0 to trigger this in the first place. That's not something I'd seen before. I thought that was really clever. There's just some points when you're looking at malware, you just think, like, I really want to sit down over beer and talk to the people that wrote this, right? And every now and then you'll just see this kind of stuff. I was like, oh, that's, all right, good on you, Mr. Malware Author. That was pretty clever. And if you break out all the VBA code into the different files it's loaded in, which is fairly typical in VBA, you have different modules with different functions in them. I'll have those broken out. Here's the entropy of each one. 3 and 5 here, I guess the red doesn't show up too well, but those have malicious code in them. And I mean, that has the lowest entropy, that has the highest, and so the highest entropy is in a module with absolutely nothing malicious in it. All right, so they've loaded enough normal-looking stuff in there that's any kind of static analysis of the randomization of that code is not going to hit on this guy. How can we catch it? Well, you can still see that the code is trying to open stuff. Right? You can still see it's trying to launch other things. We saw those character function in excess. Right? So if you see a bunch of those functions in a short time, you can pick those out. All right? So you could do regular expressions looking for a number of those functions in a short time. You can see that it's running code from a DLL. Right? Once you decode the stuff, it's calling other functions. We have base 64 strings, which again, not necessarily malicious, but certainly a common way to obfuscate code. So kind of suspicious there. And again, we see a lot of the stuff that we use. There's, of course, always a possibility of putting together like a CLAM or a YARA signature to find this kind of stuff. Because this stuff does get reused. Once I found it, of course, next thing I do is Google, right? So go back and look at Google, and turns out this method has absolutely been used before. So just thank you everyone who posts crap to Pastebin. People had dumped malicious code out of Office documents that had the exact same techniques. Those are in Pastebin. So when I went and Googled for it, others came up. So that method of using those same crap functions, right, edit customer and all that stuff, that appears in a number of different malicious documents. And the evil part, this stuff, basically the same, but all these variable names and all of the which part gets randomized and character stuff, that was randomized. So I found a few different documents that had the same filler code, but all this stuff was randomized in there. So if we do find this kind of stuff, we can start to build signatures to look for, okay, I know malicious authors are using the same filler code to wrap around their malicious code. And yeah. What else? There we go. Okay, so example 2. I asked the question earlier, what language transcends an individual language, right? Which, of course, is something if you wanted to randomize code that's not going to stand out to, say, someone who speaks a different language, you would have to take that into consideration. I had thought about the question in theory. People writing malware had an answer. So again, once I went to one of those super low entropy ones, grabbed it, okay, let's take a look at what the bad guys are doing here to get around my very clever detection here. And take a look at this one. So what transcends language? Names. Names get used a lot across different languages. And sure enough, I've been quite outsmarted here. This is actual malware. I found they are using, instead of randomized variables, they're just picking names. It might not be the most common names. I don't know if there's a lot of Haywoods out there. But you can see there's Haywood and Gaston, Nolto, right? So they were actually using, so instead of randomly generating from character a random string, they are randomly picking from a list of names. Because these are not going to show up as weird. So we see a few different ones. There were enough like long ones, like this one was long enough that I was able to Google, and again, I found a number of different malicious documents, like on Pastebin or like in where the strings had been indexed in like VirusTotal. So there are a number of documents that use this randomization function out there. Right, so this is being acted, and it's not the exact same functions. They are randomized. So we know now that someone is literally re-encoding and re-randomizing the same malicious code with different names when they send out new versions of their malware in order to get around this sort of anomaly detection. Right. So they got us. The bad guys are constantly working on getting around us, so despite me wanting to take credit for having this clever way of detecting malware, they're still getting ahead of us, right? Oh, by the way, what happens after that malware runs? Once you open the document in the right version, it executes. Well, you see it downloaded this file, right, this executable, and then, oh, by the way, the user agent, I'm going to show you that. You're not going to believe it. The guy the malware author totally gets what he's doing here. So here's the PCAP associated with that malware running. And we saw it downloading this stuff with HTTP, so I've narrowed it down to that. And then let's follow that stream. All right, so get, and then there's the user agent string. Yeah. So he's randomized everything. Even the user agent, not even faking that. The user agent going out there, what's your web browser? Arnaldo. Okay, here's your malware. Right? So, not a legitimate web browser, but again, something else. He's just randomized, again, with the names he's pulling from a random dictionary. Right? Okay, then we saw, it changes the autoexec.bat to run itself. And then we saw more communication with his IP address. And then I was able to, again, search the threat intelligence database and find a number of different samples, a number of different techniques of encoding have all been talking back to that same IP address, right? So it was looking bad. So we keep going around, right? As we'll come up with new detection, but again, the bad guys are working on it too. So I'm not going to say that, okay, the detection I just worked out is already surpassed. If you go and look at the actual data, I mean, a random sample, most of the malicious code we have is there in the middle, is going to be past the threshold I've identified as picking out randomized code. So, yes, there are definitely some smarter guys out there who know how to get around this stuff. But if you do use this method, we are going to be able to kick out a lot of commodity crap. Right? And at the end of the day, that's what you're trying to do on a blue team, is get rid of most of the noise so you can focus on that advanced stuff and actually find what someone clever is working on, right? So, yes, I've showed you how to get around it. Yes, I've showed you that people writing malware have already figured this out, but still useful, right? For narrowing down the amount of noise you have to dig through and finding some samples that you may want to spend some more time with, right? So, regardless of stupid build. All right. Yep. Right. So, but that's how it goes, right? If you're on a blue team, that's the reality. You have to adapt with the times because the malware is going to. All right. So that's the end of the data I have put together. If there's any questions, how much time do we have? Yeah, I got a few minutes. So yeah. So that came out to be about like 4.5, 4.7, which was not very different from non-malicious code, right? So like I did a sample of like every VBA script and every non-malicious like Python script and things I had like on my laptop. And those all came out to be like 4.5, 4.7, right? So, and then that was statistically different than the malicious code, which is about 5.2. Right, so if we measured that, anything like 5.2 or more has likely been randomized. So, but yeah, these guys, they can do it. And then there may be other tricks. Like you might be able to do like a rolling measurement, like break the file out into different parts, right? Because there were functions in there that were clearly randomized, right? If I measure the entropy of the entire VBA code, I get 4.7. But if I were to do it function by function, we would actually identify the malicious one, but when you sample a smaller bit of code, you also have way higher, your standard error is going to be a lot higher because you're measuring less data. So that may focus down on it, but you would have more false positives doing it that way. Right. Does that answer your question? Yeah, absolutely. I mean, it's not computationally intensive. You could do a few different ways, maybe turn that into a fuzzy fingerprint and start data mining that, right? So there are definitely ways you start to cut up that to measure the entropy. And that's worth exploring once I get more samples processed to start looking at it from a more like big data standpoint. Yeah. Any other questions? All right, well, thank you for coming out and hearing me so early in the morning, and thank you to everyone who organized the conference. For an indie conference to work over this many days is actually impressive. You guys are obviously working hard to keep this thing organized, so thank you. I hope you enjoy the rest of the conference.